We're modeling extrudability of HVAC&R alloys. And for those who don't know, HVAC&R stands for heating, ventilation, air conditioning, and refrigeration. I'm Oscar Thompson. My teammates are Conor Rork, Jacob Behrendt, and William Bogan. Our advisor is Dr. Paul, and our sponsor is Mika Clark. Brazeway is a direct aluminum extrusion company providing tubing for HVAC&R applications. The image on the left shows one of our nominal alloys given to us by Brazeway, being our 3102 extruded tube. And the picture on the right shows HVAC tubing being used in heat transient applications. Brazeway uses a direct extrusion process. It heats aluminum billets and forces them through a heated die. Essentially, direct extrusion is preheating a billet, pushing it through a complex die, and getting a complex part from it. And in our case, that is aluminum tubing. Extrusion simulations will save on raw material, increase die lifetime, and increase revenue. It was found in studies that without simulations, experimental alloy development can take up to 100 to 150 cycles. With extrusion simulations, that was lowered down to 6 to 10 cycles. As well as that, being able to use extrusion simulations allows for a reduction on raw materials, utility costs, and production costs. Brazeway wants to increase throughput without inducing hot tearing defects. One of the parts of our project was making developmental alloys off our 3102 alloy, which essentially involves expanding the process window because we want to run hotter or faster. That ends up having more friction, which can induce hot tearing if it exceeds the solidus temperature. And one of the things we're trying to focus on is creating alloys with higher solidus temperatures. Through our project, we had 3 goals in mind. I'll kind of give a rundown of those. Our first goal was to develop and validate material cards for Inspire Extrude. Our second one was to develop new alloys that have higher solidus temperature. And our third goal was to increase the alloy's resistance to hot tearing and heat checking.
So after obtaining thermo-mechanical data from a hot ISO-T testing or Glebel test, we were able to develop material parameters that were used in Inspire Extrude simulations. We then decided to validate that model with a real-life extrusion trial. We did find out that friction does play a large role in our simulation, as our extrusion ratio is extremely high at 225. So we did have to adjust our friction coefficients, but that does give us a better correlation to real life. Also, in our alloy design, we decided to decrease the manganese content and silicate content, as well as varying iron. That provided a 8 to 9 degrees Celsius increase in our solidus temperature. We also did some more Glebel testing and flow stress testing on our first and second alloys. And based on this graph, we can see that the flowability is pretty comparable to the baseline 3102 at high temperatures. However, as the temperature decreases, that flowability does decrease. Even with that decreased flowability, though, we did run the extrusion press at its maximum speed of 30 inches per minute. We did not see any significant hot checking or heat tearing. So in conclusion, our model was successfully created and validated for Brazeway. Our alloys did in fact have a higher solidus temperature, so goals 1 and 2 are completed. Goal 3, even though these alloys had reduced flowability, the alloy did not experience any significant defects. So this should give a good value to Brazeway, and we'll have to see what they do with that in the future. Thank you for taking time out of your day and listening. Thank you.